Thank you for being back. As you will recognize, we are full to capacity, and it does take some time to move this number of people up and down stairs and around the building. So thank you for your help. We now have a talk from Sir Michael Atiyah, former president of the Royal Society of Edinburgh, amongst other things, but of course that's quite the most important role you've ever had, Michael. He's also been president of the Royal Society in London, and lots of other things. He's going to talk about James Clerk Maxwell's influence on mathematics.
Thank you, President. Well, let me first say two things. As you know, Clerk Maxwell did not restrict himself to one field. He sailed across many oceans into poetry. I may not get into poetry, but I will not restrict myself to mathematics. Secondly, I had to congratulate the organisers on this brilliant start to the conference with two magnificent talks by Peter Higgs and thanks, Speaker. My memory goes at this stage. Sorry. And they were both brilliant talks, as you both recognise, and they couldn't have been better introductions to what I'm going to say. And in fact, it makes life a lot easier for me. Peter Higgs and I are close in age. I think I'm 1 week older. That's close enough. And the only difference is that he spent most of his life doing physics. I spent the first half of my life doing mathematics. So I'm a latecomer in terms of physics. So in that sense, you'll see that I have to follow in his footsteps. And his talk that he gave was such a brilliant survey of the history of physics. It makes it very easy for me to follow. The next talk followed up in the same style. So really, all the work's been done for me, and I congratulate the organisers, I'm not one of the organisers, on producing this marvellous introduction to what I want to say. So, where do we start? Well, I got a lot of slides here, and so that's my title talk, which I'll move rapidly on to, and then I can talk about locations. Here we are in Edinburgh, and there is the Maxwell Statue, with which I was involved. Next, down below, we have Trinity College, Cambridge, with the statue of Isaac Newton, and next door, the bust of Dirac, all heroes of mine. And down below, there's a picture of Bristol with SS Great Britain. You may not know why it's there. That will become apparent shortly. Next slide. This is a picture of famous names. People who have influenced me and influenced many other people. On the left is the list of names. On the right is the areas they affected. Newton, gravity, Maxwell, light. Hodge was my supervisor and went, like Dirac, went to Bristol and St John's. So that's why the Bristol comes in. And he worked in geometry, and I'm his student. And Dirac, I attended Dirac's lectures, and Dirac, I've given him insight, I think is his field. Insight. Insight is a very good word. It indicates much more than just mathematical skill. It really intuition. Now I'm going to start with some elementary geometry. Now here is a picture which you might recognize. It's drawn on the plane, but you imagine it's a projection from 3 dimensions, and what you see is a projection of a cone, 2 cones, one on each side, and cut by various planes. Along the bottom, if you cut that by a plane, you get an ellipse. Well, you get a circle in that form, but if you tilt it, you'll get an ellipse. Along the side, you'll get a hyperbola. The one I've drawn is the most perfect hyperbola, but if you tilt that, you'll get hyperbolas with different shapes. And along the edge, there's the lines which are tangent to the cone. They cut the thing into parabolas. So the hyperbola, the ellipse, and the parabola, which are very important things in mathematics and physics, are all seen there in a very simple picture. I hope you're still with me. This is not going to get much more difficult. Now, here I talk about directions. You imagine you starting off at the point 0, then you can go in 2 different ways. You can go to +1, or you can go to -1, and you can go, that's what we call real numbers. And +1 and -1, well, they all go back to somebody called Robert Record, who invented the equal sign. And you could say the equal sign was the beginning of algebra. But instead of going from just a +1 and -1, you can remember there are these complex numbers which you already had class on from previous speakers, you can go up to I or you can go to minus I. Already you've got 4 points round about the 0, which you can think of as standing up in different directions. Then actually going on beyond complex numbers, you have the ideas introduced by Hamilton, the great mathematical physicist, who discovered the quaternions, where besides having I, you also have J and K. And there you have, in a nice diagram, all the great contributions of the mathematicians of that era. And if you think of those dots as standing up in space in different directions, if you're a chemist, you can think of those as the locations of atoms. You can think of, those of you who are chemists might recognize the sort of molecules for salt, or if you're other kind of chemists, you might recognize methane. These are templates for chemistry. And when I say they're templates, I really mean they're templates. This is not just some fiction, not just mathematical symbolism. You can imagine that as being exactly what you see in the laboratory. And then we move up to the geometry, dimensions. Well, on the left-hand side, I've written down the dimensions. We all start off living on a line. We've gone from the positive real line to the negative. We have the real line with plus and minus. We moved up into the complex plane, as you heard, where we have the circle of rotations. Then you can go up into higher dimensions, three-dimensional space, where the boundary is a two-dimensional sphere, and the four-dimensional space, with the dimensions go up one at a time. And Hamilton was trying to go beyond the complex plane to do something in dimension 3. He realized that you had to do 3 and 4 together. That was his great insight, which is recorded somewhere on a bridge in Dublin. So this is the history of dimensions in mathematics, and it has great impact in physics, because as we've already heard, the complex numbers play a very important role. Now I go on to equations. As you know, mathematics depends on being formalized in terms of equations. And the equations, of course, use the algebra. Algebra was a great contribution of the Arabs. Something goes back into India and the Chinese. And I've written down here some very important equations. These are second-order equations. They involve squares. So the second line says x squared minus c squared t squared equals 0. And you can recognize in there, well, anybody will recognize what you want. Speed of light, c, and so on. And you can recognize that it also factorizes into x minus ct and x plus ct, which is Dirac's contribution. The c squared is the number that appears there, can vary from minus 1 to plus 1. And as it goes through that, it goes to a singular point when c equals 0, which is what physicists call a phase transition. X and t can stand not only for one variable, for many variables. X can stand for a whole string of variables, as many as you like, x1 up to xr, depending what dimension you're in, and t can similarly stand for t1 up to ts. And c, similarly, will be paired off with that, has also to have the same number of variables. All this is elementary algebra, but it's the algebra that underlies the equations of physics. The second-order equations, first of all, start off as algebra, but then they become analysis. The second-order equation most familiar to people is the Laplace equation. It's an example of what's called an elliptic equation because of the ellipse. Then there is the wave equation down the bottom, which is called hyperbolic because it reminds you of the hyperbolas. And on the way, you get what's called the heat equation, which is parabolic. It's one in which the second-order terms dropped out, and you're left only with a linear term for d by dt. Those are the fundamental equations of classical physics, and they correspond fundamentally to the basic bits of geometry that I told you about. All very obvious, all very straightforward. Everything knows, you all understand all that. You learned it at school, or you learned it this morning for the lecture. Now let's go make it easier. That was quadratic equations. Let's go to linear equations. Everybody can do linear equations. So the first equation, if I factorize it, I would get x plus or minus ICT. It's a linear equation between x and t and c. Again, x and c and t can stand for many variables, but just think of them as one at a time. That will do. And then when you go to analysis, well, the analysis that follows onto that is precisely the Dirac equations. The Dirac equations are first order, unlike the Schrödinger equation and others which are second order. So the Dirac equations are first order, and Dirac had to introduce something to go with them, he had to introduce spinors. Now, I don't think spinors have been mentioned in the lecture so far, but they are fundamental. Spinors are to geometry, well, spinors are like the square root of geometry. So I ended up here with this catchphrase, which is to be taken seriously. It's written in a nice big letters, you can see, with colours. The colours are not accidental. Who knows what those colours are? They are the colours of the rainbow, as you recognise them. You remember I was taught the anagram of Roygbiv? Well, that's Dirac is red, and you go down the spectrum of the colours until you get the geometry. Unfortunately, the number of words in there is exactly the number you need for the rainbow. So take that seriously. The Dirac world is the square root of geometry, and the spinors are what live in the Dirac world. Without spinors, you couldn't formulate the Dirac equation. They are fundamental, and you know that it took mathematicians many, many centuries to understand what the square root of -1 is. The square root of -1, if those of you who don't know, or haven't learnt already this morning, is I, the complex number I, which was invented because they needed something for the square root of -1. So it took them hundreds of years to realize that not only was the square root of -1 useful, but in some sense you could actually make sense of it. And then gradually it became absorbed, became part of the foundations of mathematics. From there, it became part of the foundations of physics. So these imaginary things acquired a reality. The same things happened with spinors, but that took much longer. Spinors are not the square root of -1, they're the square root of geometry. Now that's a much more difficult notion. Who knows what the square root of geometry means? Well, I've been working with spinors most of my life. And I'm old enough now to have had quite a long life. And I still struggle to understand what spinors are, but I think I'm getting near the end of the road now. I think I know what spinors are, and that's encoded in that word. And the Dirac world is the square root of geometry. That is what spinors are. They are fundamental things which precede geometry. Geometry is what, as you know, came from the word meaning measure the earth. That's what the geometry was. It was more or less geodesy. Look at the earth, measure angles, distances. And Dirac's world is different. You introduce spinors, which are the square root of geometry, and if you don't understand what they are, you haven't understood Dirac, you haven't understood physics, and you haven't understood, but don't worry, very few people have. I think nobody has really understood what spinors are. We're only getting close to the end of the road now. I don't want to be premature, but maybe by the end of this morning, you will all be able to pass the test. What is a spinor? Now, the physicists know about two kinds of worlds. There is the non-relativistic world, and there is the relativistic world. You've heard about that from the two lectures this morning. Now, the non-relativistic world is the world of second-order equations. It involves metric geometry, which measures distances, curvature of space. All of these things depend on measurement. You can't measure until you've got notion of geometry. Geometry is measurement. It means measuring the earth. Now, people have known for a long time that you can have a flat earth, which has no curvature. You can have a sphere, which has positive curvature. And you can have that other more mysterious thing, which is called hyperbolic space, which is negative curvature. Negative curvature is what when you're climbing a mountain and you get to a saddle point, a pass, one direction goes down the valley, the other direction goes up the mountain. You are at the saddle point. Saddle point is a space of negative curvature where the two up and down go in different directions, as opposed to a maximum or a minimum where you're going in the same direction. Symmetric geometry and curvature are fundamental in our understanding of geometry and our understanding of basic physics. The Laplace equation, and by here, when I talk about the Laplace equation, you know the Laplace equation is the sum of squares of second derivatives. So d by dx squared, d by squared, and so on. But you can put any signs you like in, then it changes its mind. Instead of being the Laplace equation, it becomes a hyperbolic equation, and those are what are called phase changes. So all equations, all signs are allowed. And then you come to things like spectrum. If you have a Laplace equation in nice situations, you will get a spectrum, what are called eigenvalues, and those are interpreted in terms of energy levels. You've seen pictures of that before. And closely related to that, you will, of course, get the notion of mass. Mass and energy spectrum go together. The mass is the embodiment of this story. And you've heard all the lectures this morning before me told you that in many ways. Mass is associated with spectrum, which shows the energy levels, and so on. That's all part of the non-relativistic world. And the Schrödinger equation is the equation of quantum mechanics, which is again a second-order equation, but written in a non-relativistic way. All these equations mean that you've separated out space and time. They're all fundamental in classical physics, but then along came, of course, geniuses like Dirac. And in Dirac's world, we're dealing with a relativistic world. A relativistic world is linear. There are no second-order equations, they're linear. The geometry is no longer metric geometry, it's what we call conformal geometry. Conformal geometry is concerned with things like angles, areas, and so on, not with distances. Distances are metric, areas and angles are conformal. So when you go onto the Earth and you look at different latitudes and longitudes, you're really using conformal geometry. Conformal geometry is more, in some sense, more, how shall we put it? It doesn't involve measurement in the sense of distance. Distances are not involved in conformal geometry. Dirac equation, similarly, is not concerned with distances. It's concerned with conformal stuff. The Dirac equation belongs to this linear world, and it is consistent with conformal theory. When people mention the conformal invariance of the Maxwell's equations, that was conformal invariance, which actually has a very interesting history. It was discovered independently by two people in Cambridge, and gradually became realized that was important. So the Dirac equations are conformally invariant, and coming out of that, the most important notion in a relativistic world is not energy, it is entropy. Entropy, or information, is the analog in the relativistic world of the non-relativistic notions of energy. Energy and entropy are intimately linked, but they are not the same. And the best example is because the lectures before me were so brilliant, they told you everything. I don't need to repeat things because they were so well explained. All I'm going to do is to look at them from a new point of view. And the next slide really is the only two slides you need to remember in this lecture. The one that's following and one later on. So the next one, if I get it right, is this one. Now look carefully at this one. Look carefully at it. This is the one that you have to remember. It is vitally important. Now what does it have in it? I've written down gravity. Because so far, as people have pointed out, in conventional physics, gravity is to a great extent ignored. When you do atomic physics, you don't worry about gravity. Gravitational forces are so weak that it doesn't affect the nucleus or the atom. Mistake. It does. Gravity is all around us. We can't escape it. The reason we can't escape gravity is, as you know, gravity is only one direction. There is no anti-gravity in the obvious sense. So gravitational forces accumulate. And since the universe has matter in it, all that matter produces a gravitational force which is everywhere present. You cannot escape gravity. Only escape gravity if you go into a world where there is no gravity, where there is no mass. That's a very dull world. So you cannot escape gravity. Gravity is always there. It is background. You can't help it. So gravity is very important. And the one place where I'm, differing slightly from my predecessors is to emphasize the fundamental role of gravity. It has to be there. Everything hinges on gravity. And I'll try to explain a bit more. Now, in the middle, I've got what is, well, you can take of it if you like. If you think of it one way, it's the Archimedes screw. Think of it the other way, it's the double helix. They're the same thing. Reflect on that. This is a picture, and there is a movie that goes in it. You can get this on the internet. And there is a movie version, but it was a little bit beyond the technology of my very able assistants. But it does actually show it winding around. Now, so let me digress a moment, since I have time. let me tell you, what is the Archimedes screw? The Archimedes screw is, of course, named after Archimedes. But before Archimedes, it existed long in the past. If you go back to Babylonian times, there were the Hanging Gardens of Babylon. How were they watered? Think about it. How did you get people to get water up from perhaps the Euphrates, which is quite a way, up to the Hanging Gardens? I'm not sure how far the Euphrates is from Babylon. I have to look at my geography, but I'm sure there are scholars here who know that. Well, the answer was that you use the Archimedes screw. And that was a device for pumping water from a lower level, the river, up to a higher level, which could be agricultural field if you're a farmer, but it could be the Hanging Gardens of Babylon. Of course, in those days, the energy to pump that water up was probably produced by slaves. You whipped your slaves harder and harder, and they pulled round and round, and eventually the water got up. So you turned the energy of the slaves into the entropy, which is driving the water uphill. So, of course, later on, Archimedes came along with a much better device. When I was a boy, I used to go on the Nile steamer down the Nile. And the Nile was a long way beneath the fields which where the peasants farmed. So they needed to get water from the field, from the river, onto their fields. So they would go down with buckets and carry up a lot of work. Archimedes' screw was a brilliant device. He put a wooden contraption into the ground, which was essentially this helix. The water down the river, the Nile, came down, entered the bottom of the spiral, and then the pressure of the water gradually drove its way up to the top till it landed on the fields. Meanwhile, the farmer was sitting, smoking his narghili, enjoying himself, doing no work. He was being irrigated, his fields, for no cost. It was a most ecologically brilliant invention, long before modern ecology said we shouldn't be burning carbon and so on. There was no carbon. But where did he get his energy to pump the water uphill? It came, of course, from the Nile. The Nile was going downstream. Why was it flowing? Of course, because of gravity. If there would be no gravity, there would be no fall. The water would not be stagnant. It would not go up. So what the Archimedes screw was doing was converting the energy of gravity into the entropy required to pump water uphill. Simple as that. But it was a genius of Archimedes to realize that this is what you do. This is the shape that you have to employ to do it efficiently. This shape, in mathematical terms, has technical terms. It's called a conicoid or something like that. And it's a very remarkable surface. If you cut it open, it turns out to be the only other ruled surface on the plane that is a complete surface. And you have the plane and you have this thing here. This is a universal object, mathematically. It's absolutely unique. And Archimedes used that beautifully to transform gravity into entropy, driving water uphill. That was a stroke of genius. Archimedes was, amongst all my heroes, well, certainly a candidate for #1 slot. You know, you take a vote amongst public. Who is your #1 figure? Well, we can all have our heroes, Maxwell, Dirac, but certainly Archimedes is up in the top rank. And now, if you look down below, you'll see the word double helix. It wasn't until I started looking at this picture that I realized this is actually exactly a double helix, word for word. You look into it, the geometry of the double helix is all here. There are 2 strands of DNA going in opposite directions. If you're a molecular biologist and you just study this, you realize that Crick and Watson didn't have done that any hard thinking. All they needed to do was to go back and talk to their Iraqi colleagues who did archaeological digs in Iraq. And from that, they would have found it out. Well, I've got on the side here a picture of the Escher drawing, which shows you how you can convert water falling downhill by a bit of clever trickery due to Roger Penrose. And that is the trick, to convert the waterfall into... And there's a nice story with that, but I better stop because my time is running short. But don't forget this slide, okay? That's the most important slide, except for 1 or 2 little ones, which we're going to follow now. This one here. I'll go through it fast, but basically, here is the Earth. Sorry, there's the Earth, and there's the Sun. They're connected by a little strand, and I've got colors to indicate. And this strand is actually what physicists call a string. People talk about superstring. That's the string. You start off with a world which is symmetrical at the beginning, and according to the basic idea of Dirac, the time flows to produce asymmetry. And these ideas are also developed by Kepler and Newton. And next, coming to the end, the next slide, this is science. I've taken a big picture of science. Science goes a different... We live somewhere down here. So on human scale, they're here. Inside us, there are cells, there are viruses, DNA, molecular biology, molecules, atoms. These are all the strands of science at different levels. And these are scales. We are actually somewhere down here, but it's convenient. Most scientists talk about this level. If you're a chemist, you're here. If you're a biologist, you're here. Molecular, still atom. And of course, you can go up as far as you like. We don't know how far you can go, but you might, and you can go the other way as fast as you like. And now, I think this is the last slide. This is the one that attributes all the great people in the past. Well, you take your pick. They're all famous. Of course, I've highlighted Maxwell. But we have highlighted a number of famous women. Rosalind Franklin, Noreen Murray. And finally, I'd end with this quotation. It's more important that an idea should be fruitful than it should be right. I think I'll end there. Thank you.
Thank you very much, and I love that last quotation. It's wonderful.
I'm going to join you over here.
Yes, come and have a seat.
Is that this one?
Whichever you fancy.
The nearest one is.
So once again, we have an opportunity for questions. If you could raise a hand, and we'll get a microphone to you. Or comments, doesn't have to be questions.
Michael, I'm interested in your comment about the role of entropy. There's an open problem in the world of thermodynamics, which is non-equilibrium thermodynamics. So to what extent are ideas in non-equilibrium thermodynamics relevant to this picture you have?
Well, there are two situations in physics, equilibrium and non-equilibrium. Of course, if you start with non-equilibrium, you have to let something flow, maybe temperature, maybe time, to reach equilibrium. And that flow is, of course, a dynamical process. And that's a fundamental part of physics at all levels. You're not in an equilibrium state, usually. You're coming out of one equilibrium, going to another equilibrium, and the whole host of dynamics is, of course, involved. And that dynamics can take place at many levels, many kinds. You're absolutely right. Dynamics is a fundamental part. We don't reach the end of the story. We don't get to a stable state until we're dead.
And even then, the atoms go round again.
Thank you.
Yes, right at the back, please.
Michael, I'm interested in what mathematical structures did Maxwell construct or invent to some extent, and how did he invent these structures or come into being these new structures?
Well, I'm giving another lecture tomorrow in the same building under a different heading, and the answers will be given there.
And you're writing it tonight.
More almost, but I could give you a quick answer. In some sense, mathematics creates itself, and so does everything else in the universe, from life onwards, upwards. And it creates itself on some simple principles, which inherently are mathematical. They are the principles of simplicity and minimum expanse of thought. You learn one trick and you repeat it infinitely often. That is how life began, that is how physics began, and we're still doing it now. The same idea permeates all physics, all science, all biology, all mathematics. It is the idea of duplication in the simplest possible way. You reflect on that, and you won't need to come to my lecture tomorrow.
And maybe that's a suitable point for us to leave this particular talk and move on. Thank you very much indeed, Sir Michael, for a wonderful overview.